I'll try a little experiment and see if I can get this entire lecture in a video format. In the past, we've all seen parametric equations defining plane curves, and that should be in Chapter 9, Section 2 of this particular text, but you've probably seen it in some other place. And when we define vector-valued functions as opposed to plane curves, it's almost the same. It's not a lot different, but a little bit. The extra dimension, though, now we're in 3 dimensions, it adds a few nice changes. So a space curve is a set of all ordered triples, f of t, g of t, h of t, together with their defining parametric equations, x equals the f of t, y equals the g of t, z equals h of t, for continuous functions f, g, and h, and t is some parameter in some interval I. It's very difficult to draw these graphs, but I can do it with my nice software. Useful way to notate and understand such curves is to use the concept of a vector-valued function. And first we'll look at a vector-valued function in R squared, in 2-dimensional space, and then we'll look at a vector-valued function in R cubed, that is to say, 3-dimensional space. And the component functions are the f and the g, or in the 3-dimensional case, the f and the g and the h. I'm just using those letters. You can use whatever you want. But they're real valued functions of the parameter t, and t, of course, is in some subset of set of real numbers. Okay. Component notation would be, instead of saying, like with the I and the j, like this is ftj, or fti plus g of tj plus h of tk. For I, j, and k, the unit vectors you're used to, I, unit vector in the x direction, j, a unit vector in the y direction, k, a unit vector in the z direction. So component notation would just be like to put, notice that it's not round brackets, it's like carets. It's like a greater than and a less than sign, but in context it could be given to you like that. It's the same. This vector valued function is the same as this vector valued function. It's just notated a little bit differently, but it is exactly the same thing. So they can be used to trace the path of the space curve, as I hope these following examples show. The first one is entirely in the xy plane, because you notice I don't have a k. So r of t is 2 cosine ti plus 2 sine of tj for 0 less than or equal to t less than or equal to 2 pi. And that should be fairly easy to understand. Chapter 9, Section 2 would remind you. What we have is x of t, the x-coordinate of a point is 2 cosine of t, the y-coordinate of a point is 2 sine of t. And so, to simplify this one in particular, because we have such nice component functions, cosine of t and sine of t, we can solve for cosine and sine of t using the trig identity cosine squared of t plus sine squared of t is equal to 1. You should be able to see this describes a circle of radius 2. So the graph starts and stops at the green dot. Here's what I'm saying. If you say x equals 2 cosine t and y equals 2 sine t, then x over 2 equals cosine t, y over 2 equals sine t. Maybe I should write that. If x was equal to 2 cosine t, see, and if y was equal to 2 sine t, then x over 2, oops, I didn't mean that. I could delete that too. Hang on a second, I'm working on it. This should be x over 2, so x over 2 is equal to cosine t, and similarly y over 2 is equal to sine of t, and then when you square them both, see, you get x squared plus over 2 plus y squared over 2 equals 1, so we got a circle of radius 2. Now, I know you're thinking that's like an ellipse, and it is like an ellipse, with the exception of the fact that the a and the b are the same, so it's an ellipse where the shortness and fatness are equal. And so it is, in fact, a circle of radius 2. And we can actually think about plotting points. If t was equal to 0, then the I component, or the x part, is 2 cosine of 0, so the x part would be 2. It would start here. And by the way, the j component, of course, sine of 0 is 0, so it would start here. And then as t grows, like t would maybe move to, let's say, pi over 4, then this is 2 square roots of 2i and 2 square roots of 2j. So we'd be maybe up here somewhere. So we're moving along this purple graph. This purple graph is actually, in 2 dimensions, the graph of this vector valued function. So as I said before, it's not really a whole lot different from parametric equations. And the parameter, 0, t going from 0 to 2 pi, puts a direction on this. I don't know if you can see my little purple arrowheads there, but that gives that one a direction, okay? So that is the graph of this particular vector valued function.